You know, when you look at a skyscraper, you see this triumph of steel and concrete, right? But the very first battle, the one that makes all of that possible, happens way down below the ground, in the dark. And it's a fight against an opponent that's relentless and literally everywhere: water. Today, we're diving into the story of that fight. It's a pretty simple question when you think about it. You dig a deep hole, especially somewhere with a lot of rain or near a river, you'd expect it to fill right up. So why doesn't it? Well, the answer is this massive hidden engineering effort that is constantly at work, just out of our sight. And there it is, our antagonist, groundwater. And we're not talking about just a puddle after a storm here. This is a huge, saturated zone of Earth under our feet, and it's always trying to reclaim any empty space we create. Managing this is one of the first and most critical challenges in any big construction project. So, if you're going to win this battle, engineers have to really, truly understand their enemy. What exactly is this threat, and where does it all come from? Okay, it all starts with something called the water table, and the name itself is a fantastic analogy. I want you to think of it like the surface of water in a glass. If you dig down and you hit this level, you've reached the point where the ground is completely full of water. Every single crack, every pore, it's all saturated. That's the groundwater zone. So what happens if you just don't control this water? Well, the stakes are incredibly high. We're not just talking about muddy boots. An excavation can flood completely. The walls of the pit you just dug, they can collapse. The pressure from the water can actually push up on a finished foundation from below, creating massive instability down the line. It's a force that can bring a $1 billion project to a grinding and very dangerous halt. Which brings us to the main goal for any engineer. Before anything else can happen, they have to achieve one primary objective. They have to find a way to build in the dry.
And that's where this whole process, called dewatering, comes in. And believe me, it's way more sophisticated than just bailing water out of a leaky boat. This is about strategically removing water from the soil itself, actively pushing that water table down to create a stable, dry zone. It's about taking complete control of the underground environment.
All right, let's start with the most direct approach. How do you get water out of a hole? You pump it, right? Let's take a look at how the simplest method, called the open sump, works in a real-world scenario. You know, the logic here is actually pretty genius in its simplicity. You dig your main excavation, and then, at the lowest points, you dig a few smaller pits. They're called sumps. All the groundwater that's seeping in naturally flows downhill into these sumps, and from there, you just pump it out. It's effective, it's economical, and for a lot of shallow projects, it's all you're going to need. Okay, let's look at a classic problem. This is a site for a new commercial building. They've started digging, but the water table is incredibly high, less than a single meter below the surface. The result is what you see, a muddy, flooded mess. You absolutely cannot build a solid foundation on that. So first things first, they bring in the pumps, they're placed right into those sump pits we talked about, and they get to work, pulling all that collected groundwater up and out of the site. And just look at the transformation. As those pumps keep running, the water level just drops and drops, turning that muddy mess into firm, workable ground. The construction site is literally emerging from the water, creating that essential dry base they need for the next step. And this is the payoff. With the site stable and dry, the real work can finally begin. They can pour the concrete for those column footings, totally confident that the foundation they're building is on solid, secure ground. It's just a perfect example of how dewatering makes modern construction possible. But what happens when you need to go deeper? Or when the soil itself is less cooperative? Well, that's when a simple sump just isn't going to cut it, and engineers have to bring in the heavy artillery of dewatering. So, we're basically looking at two main advanced systems. The well point system is kind of like sticking a whole bunch of small straws into the ground, all connected to one big header pipe. A vacuum pump then sucks the water out. By contrast, the deep well system uses fewer but much bigger and deeper wells, and each one has its own powerful pump at the bottom that pushes the water up and out. Now, that well point system, it's got one major limitation. A single setup can only lower the water table by about 6 meters, or around 20 feet. If you need to go any deeper than that, you actually have to build entire new systems in stages, creating these giant steps down into the earth. And installing one of these deep wells, wow, it is a whole project in itself. First, you have to drill a deep borehole.
Then you install a casing in a screen. That's kind of the skeleton of the well. Then you have to pack a special filter around it to keep all the soil out. And finally, you lower a massive submersible pump all the way to the bottom. It's a huge undertaking, all just to get ready to start pumping.
But what about the really tricky soils? I'm talking about fine silts and clays. Water just clings to these tiny particles and doesn't flow easily, so you can't just pump it. For this, engineers had to come up with something that honestly sounds like it's straight out of science fiction. Check out this quote, because it reveals a physical phenomenon that is just bizarre. It turns out that if you apply an electrical current to wet soil, you can actually force the water to move. This really strange principle is the key to dewatering in what would otherwise be impossible conditions. Okay, so this wild process is called electroosmosis. Here's how it works. You drive a positive electrode and a negative electrode into the ground. When you run a direct current between them, the water molecules are literally forced to travel through the soil, away from the positive side and toward the negative side. So you just set up collecting wells at the negative end and pump out water that would have been completely locked in that clay. It is absolutely fascinating. But of course, running live electrical currents through a wet, muddy construction site, yeah, that comes with some pretty serious risks. The voltages can go up to 100 volts. Everybody working in the area has to be in rubber boots, and there are super strict rules about not touching the equipment. One wrong move with a piece of heavy machinery could create a short circuit, which could be incredibly dangerous. This is high-tech, high-stakes work. All right, so we've seen everything from simple pumps to literally electrifying the soil. Let's zoom back out for a second and see how all of this connects to the world that we live in every single day. And here's the big takeaway, the thing to remember. Every deep basement, every subway tunnel, every dam, and the foundation of every single skyscraper, they likely owe their existence to some form of dewatering. It is the invisible, foundational work that creates the stability we need to build the modern world. Without it, our cities simply couldn't exist the way they do today. Dewatering is just one example of this hidden world of engineering that quietly supports everything around us. And that really makes you wonder, right? What other invisible systems are at work right now, keeping our world standing?